And finally, with waves, what we're going to do is we're going to look at the behaviour of light in terms of waves, rays and photons, and see if we can exploit it some way to do something useful for taking a measurement or for material processing or something like that. And so one of the useful things that we can look at is the change in frequency that we get when the source of the wave is moving, or if the thing which is measuring the wave, or the observer, is moving. If they're moving relative to each other, then we will get an apparent shift in frequency. So I'll try to represent that here. If we've got our fixed source, it stays where it is, and it's emitting all these peaks. And let's just think about it as sound waves just now, because it's more easy to think about Doppler in terms of the sound. And this is my observer, who is represented by one very large ear. And if that observer is moving towards the source, then what we will see is we get a higher frequency being perceived and measured. This is referred to as a blue shift in optics. In sound, what we're getting is a shift in frequency. If the ear was moving away, then we would get a lower frequency, referred to in optical applications as a redshift. So you can think about this in terms of the emergency vehicles coming towards you or going away from you. And as they come towards you, the pitch is high, and then as they just pass you, then the pitch drops down low as you go past it. As they go past you, sorry. We get the same thing if the observer is stationary and now the source is moving. So this initial wave here at t equals 0 came from that point. In the time that it takes to go from peak to trough to peak again, the source will have moved on a certain distance and started a new wave from a new location. And so what you can see is that if the source of the wave is following in behind the wave, then the wavelengths get shortened or scrunched up in front of the source, and in the opposite direction gets stretched out from the source. Shorter wavelength means higher frequency. Longer wavelength means lower frequency. So we get the same effect irrespective of whether the observer is moving or whether the source is moving. We get the same Doppler effect. We also get this in light waves, and that's interesting because it allows us to figure out things like the universe is expanding. If we look at the light coming from various stars, and we know that some of that light will be because there is hydrogen in the star. In the lab we can look at what frequency we expect the light coming from the hydrogen atoms is occurring, and then we can look at the light which is coming from the stars, and what we see, it doesn't matter which direction we look in, what we see is that the light is all red shifted. It's all looks as if every single star is moving away from us. Now that doesn't mean to say that we are the centre of the universe. It just means that the whole universe is getting bigger and we're all expanding away from each other. So if you think about a series of dots on the surface of a balloon, if I blow up the surface of the balloon, everything moves away from each other, and you then would see for each of those dots a red shift for any radiation which has been emitted by them. Other examples where this can be useful is that when we have the light coming from some particular gas, so if we, for example, with a fluorescence tube or a neon tube, if we have an atom and that atom is giving out some light, if it's moving towards us, then the light will look blue shifted, and if it's moving away from us, it will look red shifted. So that tells us then something about how the atoms in the gas are actually moving. Okay. So some of the atoms will be moving towards us. In any box full of atoms, some of them will be moving towards us, some of them will be moving away, most of them will be doing something in between, and that distribution of speeds and directions tells us information about how the gas is behaving. Ideally, what we want to have, for a laser, one single pure frequency. But if we imagine we've got our laser box, let's supposing it's just a black box and the light's coming out in both directions or in one single direction, and if it's a gas laser, in other words, if we're using a gas like neon to produce the light, then this distribution of movements that we expect in the gas will give us a distribution of frequencies coming out. So if, for example, in the gas, some atoms will be moving towards us at very high speed, that will be very few atoms out of the total, then we would expect to get the light being shifted to a higher frequency, but not very many of them. If we think about again the sort of opposite case, then again lots of atoms moving away from us very quickly, we won't see very many of them. Most of them will be doing on average nothing. In other words, they could be moving in this direction perpendicular to where we are looking, in which case we don't see any Doppler effect. So instead of seeing one single pure frequency, what we will see is the intensity as a function of frequency will have some sort of distribution of them. Now that's referred to as Doppler broadening, and that Doppler broadening we'll see can be exploited to measure things like the speed at which some object is moving, in the same way that radio waves are used in speed trap cameras. We can do the same thing with lasers. Okay. So, light moving, a moving source or a moving observer. If we have stationary, then we get our fixed frequency, and if we have motion towards, then we get a blue shift. Motion away, we get a red shift, and for everything in between, we will get some shift somewhere between these two extremes.